Meet the northern clingfish. Not the most charismatic of creatures, but this unassuming fish, no bigger than your hand, demands your respect. Why, you ask?
They can really suck. The suction device in a clingfish is its fused pelvic and pectoral fins. They form a complete disc on the belly of the animal.
This sucker enables the clingfish to hold on to the slimiest, wettest, and roughest surfaces. And it works even after the animal has died. And just in case you don't find this impressive, consider this. If you had a clingfish sucker on each of your hands, you could easily climb Mount Rushmore in a hurricane. So what gives this sucker its punch? To answer these and other mysteries of the deep, look no farther than the University of Washington's Friday Harbor Labs.
Located in the San Juan Islands, about 60 miles north of Seattle. This is a wonderful place to study marine biology because it's got relatively pristine waters.
It's here that Dr. Adam Summers and Dr. Petra Dicha study how the form of fish, their muscles, their mouths,
the body form, dictate the function. And in seeing them do unusual, surprising things, we then refine what parts of form are really important.
In the case of the clingfish, Dr. Summers and Dr. Dicha didn't have to go far.
Locally, we can find them. We can find them in tide pools, we can find them on wave-swept shores.
So during low tide, the team headed out with their assistants.
My 7-year-old daughter, she's a dab hand at catching clingfish.
They hunted for specimens, particularly under the slime-covered stones where the clingfish live.
And we'll flip rocks and explore tide pools.
Yes! 2 big clingfish. That's great. Where's the bucket?
That's a big one, yeah.
Occasionally, they even conducted tests in the field.
They can really cling.
They also gathered up food for their newly acquired specimens.
Limpets are the archetypal attached mollusk.
You gotta get them quick.
In fact, the fish's super sucker isn't just to grip slippery rocks and rough surf. It gives them the leverage to
Suck the limpet off the rock.
Back at the lab, the team took a closer look at the fish's sucker.
These are not good-looking suction cups. First of all, they're covered in obvious knobs. A wild thing is that when we look at them under the scanning electron microscope, each of these knobs is covered in tiny hairs.
The same size as the hairs you might find on the feet of a gecko.
And they're implicated in a terrestrial environment with dry adhesion. That's definitely not what's happening in the marine environment. First of all, you can't have dry adhesion in the marine environment. It's all wet.
Instead, these soft hairs provide friction.
Because the way a suction cup fails is the edges of the suction cup move in. And as the edges move in, suddenly you get a little tunnel that appears in the edge of the suction cup that causes water to fly in and boom, it fails. These little hairs prevent the edge of the cup from moving.
How important is this friction to the clingfish? To answer this, the team stuck suction cups and dead fish, who couldn't decide if they wanted to let go or suck down, onto increasingly textured surfaces. Both were then harnessed to a force sensor that hoisted them up until they popped off. While the suction cups could hold on to only the smoothest and unslimy surfaces, the clingfish's hairy sucker maintained its grip against 150 times its own body weight, and on the slimiest and roughest of surfaces. But the clingfish's sucker isn't perfect.
Clingfish-inspired adhesive systems are inherently wet. Climbing Manhattan skyscrapers on a sunny day is not going to be the area that this technology is regularly applied. It's really going to be in torrential rains. Climbing waterfalls, you should be able to buy a suction cup that would stick to the wall of your shower across the grout lines of the tile.
And as anybody who's ever used a shower caddy knows, this is no small feat. For Science Friday, I'm Luke Groskin.